This video will discuss techniques for implementing corpus-based chatbots. Corpus-based chatbots are a more recent development than rule-based chatbots, and one of their key advantages is that they don't require time-consuming manual definition of rules. So instead, the bulk of the time spent developing them is focused on discovering which architecture and features or data characteristics are able to best make use of a provided data set. Corpus-based chatbots are becoming more and more popular as large, high-quality data sets become more readily available. Rather than relying on manually defined rules, corpus-based chatbots learn mappings from inputs to outputs based on large data sets of human-to-human conversations. Data sets in natural language processing are often referred to as corpora, with the singular being corpus. And the idea is that if you give enough examples to your system of what real dialogue and subsequent responses look like, then the system can figure out how to automatically produce appropriate responses to new input that it hasn't seen before. Fortunately, there are a ton of different conversational corpora that can be used to train these types of dialogue systems. One really popular classic data set is Switchboard, which contains a bunch of telephone conversations between randomly matched strangers. Depending on your target domain, you might also choose to train your system using movie dialogue or even tweets. You can also supplement your dialogue corpus with external knowledge. This can be particularly useful if you're designing a system that will be expected to answer questions or provide facts, for example, if you're creating a virtual assistant. Some common sources for external knowledge are news articles and online knowledge repositories like Wikipedia. A benefit of using online knowledge repositories is that they usually already contain pretty nicely structured data, so it's easy to programmatically retrieve relevant facts from them. And then an additional useful quality of corpus-based chatbots is that you can pretty easily update them over time so that they gradually improve as they participate in more and more interactions. You can do this by directly using the utterances recorded by the chatbot as new training data, and there are a few privacy concerns that can emerge when you do this, so you want to make sure that you're cognizant of those. For example, you would want to make sure to remove personally identifiable information from collected utterances before using them to retrain the chatbot, just so that it doesn't end up sharing private information with other people. So getting down to more specific implementation details, there are two main architectures that you'll see with corpus-based chatbots. There are information retrieval-based chatbots, and then chatbots based on machine-learned sequence transduction. Both of these do surprisingly little to consider long-term context when generating responses. Instead, their focus is usually on generating a response that is appropriate given the immediate dialogue history. And because of this minimal contextual awareness, corpus-based chatbots might a lot of times function more as response generation systems than anything else. This makes them in many ways pretty similar to question answering systems. So I'll cover both information retrieval based and machine learned sequence transduction chatbots in the next few slides. Information retrieval based chatbots function by selecting a response to a user's utterance from a conversational corpus. So they're not actually generating anything from scratch. They're just looking at a big collection of possible responses and deciding, hey, this response seems really good. So there are two simple methods that information retrieval-based chatbots can use to select a response. In one, they can return the response to the most similar term to the current input, and then in the other, they can return the most similar term to the current input directly. So in practice, returning the response to the most similar term usually works a little bit better than the other option. The idea is that if you search through your corpus for the term that is closest to the input, and then you see what response was matched with that term, you just go ahead and return it. You could formalize that using the equation that you see here. So in this equation, we're just searching for the term that maximizes the cosine similarity between it and the input query from the user, and then returning the corpus response to that term. We'll learn about cosine similarity later this semester, but it's just a vector-based similarity function that comes up a lot in natural language processing. So if we do want to use the other strategy where we just directly return the term that is most similar to the user's input query, we could use the exact same equation from the previous slide. In this case, though, we just don't wrap our argmax function in an outer function that retrieves the response to the selected term. So there are a lot of ways that you can tweak information retrieval-based methods to improve the quality of the responses that you select. One thing we didn't really talk about with that equation from the last two slides is what Q and T look like. So in natural language processing, we usually represent words or phrases as vectors of numbers. So in this case, we'd have two different vectors, one for the user query and one for the potential term that is being considered. So then the way that we fill these vectors varies widely. It is actually a huge topic that we'll cover later this semester. But for the current time, all that you need to know is that these vectors are often referred to as feature vectors, and each individual element in a feature vector represents some sort of characteristic or feature of the data that is being represented. So you can add as many types of features as you want to the systems you create. So to improve performance with information retrieval-based chatbots, you might want to encode conversational history, user-specific information, sentiment, or external knowledge as features. So we covered information retrieval-based chatbots, and now we can move on to machine-learned sequence transduction chatbots, or as they're more commonly referred to, encoder-decoder chatbots. Encoder-decoder chatbots are basically the machine learning version of ELIZA. So they perform transductions to transform a user input into a system response, but rather than doing so using manually defined rules, they learn those rules on their own. So this idea was first borrowed from machine translation, where this strategy is commonly employed in modern systems to translate a sequence of text from one language to another. So the backbone of the encoder-decoder chatbot is the encoder-decoder model, which accepts a sequence of text as input and returns a different sequence of text as output. So beyond their current popularity in machine translation, encoder-decoder models are frequently employed in question answering systems, automatic summarization, and a whole host of other applications. And encoder-decoder models are generally built using recurrent neural networks. So we'll learn more about neural networks later this semester, but they're basically just classification models that make their decisions based on a bunch of interconnected, automatically learned functions. So recurrent neural networks consider input sequence in these functions, whereas other types of neural networks don't. So encoder-decoder models are basically set up so that you can have an encoder model, so some type of recurrent neural network, for example, that accepts a sequence of text as input and encodes it as an undecipherable intermediate representation. Then a decoder model, so for example, another recurrent neural network, accepts that intermediate representation as input and generates a sequence of text as output. So it's a really nice, simple pipeline. But then behind the scenes, people will spend a bunch of time tweaking the specific architecture of their encoders and decoders so that they're able to produce the highest quality output possible. So one downside of basic encoder-decoder models is that a lot of times they'll learn that they can get the best utility from just producing repetitive responses like I'm okay or I don't know. So one way that people will choose to improve upon these models is by incorporating mechanisms that incentivize response diversity. for example, by using different objective functions or searching through multiple possible output paths to determine the best one. A few other challenges associated with encoder-decoder chatbots are that they can struggle a lot to incorporate things that were said earlier in a conversation, and they can be kind of incoherent across turns. So one way that people solve the first problem is by using a more hierarchical structure, whereas people solve the latter problem sometimes using reinforcement learning or a different kind of neural network called adversarial networks, which basically train two models at the same time. So you have a generator and a discriminator that function as adversaries. So the generator is always trying to fool the discriminator, and the discriminator is always trying to figure out new ways to identify that the generator is trying to fool it. So overall, corpus-based chatbots offer a lot of flexibility to system designers, and they have a really great advantage in that they don't rely on manually defined roles. They also carry some additional complexities, though, as we discussed in this video. So if you're designing a dialogue system, it's important to weigh the pros and cons of both rule-based and corpus-based chatbots to decide what would work best for your specific application.